Hi guys, so today we are going to talk about one key problem with post-production of a video, that's video stabilization. Because when you are a movie director or a YouTube creator, you have to get a video that is smooth looking because it's going to be more enjoyable to watch. So to stabilize a video, we decided to add a 3 steps approach for our project. First of all, we had to analyze the motion on the video and to guess how the camera was moving when the video was taken. To do so, we used some optical flow technique that we saw in class. Then we used some motion correction using signal processing algorithm in order to find the smooth looking camera motion that is going to make the video stabilize. And then we are going to complete the border of the image that were incomplete. We are going to talk about a bit more about this later.
Okay, so to start with motion video analysis and modeling, this part is mainly composed of 2 steps, feature detection and motion estimation, and camera motion modeling. For the feature detection and motion estimation part, our aim was to compute the optical flow from one frame to another based on the frame key points. And to detect and compute these key points and the features that they include, we tried 2 different approaches. First, the SIFT algorithm, which is robust to change in viewpoints, scale and rotation, but quite expensive in terms of computational costs. And on the other hand, the Shitomashi corner detection algorithm, which is a bit more advanced than Harris corner detector, but as fast, more efficient, and used in real-time applications. Concerning the camera motion modeling, there are several methods used to describe and model a camera motion. And the one we chose to use is the affinity model, which encompasses most of the advantages of similarity model, which only consider the horizontal and vertical translation, but with the possibility to also consider the shear, as you can see below, which is dA, and basically represents the rotation of the image from one frame to another. And the affinity model is faster than the homography model, but it also has difficulty to take zooming or depth variation into account. Okay, so to continue, the other part of the motion video analysis and modeling step is how to smooth the camera trajectory. The camera trajectory is computed with the cumulative sum of the affinity model components, which are the horizontal and vertical translation plus the rotation. And then once computed, it's just basic signal processing, for which we choose to use. We tried 2 different approaches again: the Gaussian filtering method, which is weighted averaging of voxel values to suppress the high frequency, and another method with a better result that we chose to keep. The Kalman filtering, which basically is an estimation of the mean and the standard deviation of the intentional motion, which you subtract to the original signal, and a moving average after the Kalman filter to smooth even more the camera trajectory.
With those algorithms, we were able to produce a first version of our stabilization algorithm. We are quite happy with these results because, as you can see, the guy in the center of the left video, which is stabilized, is not moving. The one key issue that we had is that some black parts are appearing. How can we complete the image with some algorithm.
To solve this problem of black areas, missing areas around the image, the most simple approach would be to simply crop the image, thereby reducing the size of the image. But this is not satisfactory, as the video would have a lower resolution. So we need a way to complete the image. And the approach that we use was proposed by Matsushita et al. In 2005, and it consists in calculating new values for the optical flow in the empty areas. So how do we do that? When we have a pixel P in a black missing area, we look at the neighboring pixels in the neighboring frames and try to infer an optical value based on these neighboring pixels. The formula that is proposed is actually a weighted average of the optical flows of the neighboring pixels, and the weights are calculated based on a color distance between our pixel P in a black area and all the neighboring pixels Q. This color distance is actually a simple L2 norm in the RGB space. And this ensures that for pixels that have a lower color distance, we assume that we would have pixels that correspond to the same object, and we would have an optical flow value that would be approximately the same. To implement this strategy, we have to complete the image from the center to the exterior of the image. And the solution we have found is to implement a snail traversal of the image, which goes from the center and follows a spiral pattern until it reaches the edges.
So here are the results of our video stabilization algorithm. On the left is the raw video, on the right the stabilized one. Let's take a look. The one on the left is quite shaky. It's moving left and right, and we can see some noise. On the right is the stabilized video. As you can see, Hugo is not moving, is on the center of the video. The motion of the camera is quite slow, and it is full. As you can see, the borders are completed automatically. So we are quite proud of these results, as we only used some computer vision algorithm and not any deep learning algorithm. There are still some issues that we can try to improve. First of all, we can see that we have some noise on the border, and it can be an issue. We expect it to be clean with some, if we have more computational power, like for instance, using more frames and running and trying to average each values by its neighbors. Then we can see some glitch between some frames. It's because we are only using one frame to calculate the correction of the next one. If we use more frames, the video will be even more stable. Finally, I think that we could try to remove blur using some other technique.
So thank you for your attention. This is all for our presentation. And if you have any further questions,
or if you need any further information, please reach out to us by email. We'll be happy to provide with more details. Thank you.